my name is Michael Detwiler. I am part of the um, AMD server business unit. I'm based in Austin, Texas. Sorry, I've tried to arrange my screen here so I'm not blinding you with the light behind me. So I'm a little off center, but you're at least not blinded. So I appreciate the opportunity to talk to you guys about our products, how we view HPC, the problems we're trying to solve, specifically around specifically our products and how we can hopefully add value to your business or your organization. So I'll just kind of cut right into it. Um, so, real quickly, just a couple notes on, how we view from a strategy and from a direction standpoint, our view on HPC. From the very top down, from our CEO, Lisa Su, on down, there's a maniacal focus on execution. Execution of the roadmap, making sure that we are delivering products on time as defined. And in all markets where that's of critical importance, HPC is certainly that. There's a lot of times written into RFPs, very, very tight timelines where you need to have delivery or else there's, some penalties. And so, frankly, our execution over the last 3 or 4 years has been a differentiator for us. We've been, very solid when it comes to delivery of our roadmap and the products and the timing of those products, and it's led to some really high-profile wins in research academia, and then a lot of good wins in the enterprise or commercial space as well. So execution. But obviously, execution is only part of it. You need to have an interesting product too. So it's not good to just deliver a product on time if it's not interesting, especially to an HPC crowd. So our focus is on leadership performance. We try to make sure that we have a feature set that's attractive to the HPC community. And frankly, the execution and our product definitions in the past 3 years have led to very strong HPC adoption and cloud adoption as well. They were some of the first adopters when we first launched EPYC, first generation of EPYC in the middle of 2017. When it comes to product strategy, make no mistake, it's a very compute-focused roadmap. So if you take a look at our roadmap several generations out, it's highly focused on compute, which is something that we never want to take our eye off the ball. But also we recognize that it's not just about the hardware, and there's a heavy investment in the tool chain. So when it comes to compilers, when it comes to libraries, when it comes to profiling tools, there's a large effort and investment underway at AMD to deliver and continue to improve those products. But also we take pride in the fact that we're very open and we want to collaborate with the ecosystem. So we have a commitment to an open ecosystem, commitment to partnerships. It starts, certainly we think the silicon is very important, but we work really, really closely with our OEM partners to design platforms that are optimized from a performance standpoint. We work closely with, the OSV community. So, the operating systems, are they scheduling to in an optimized way to take advantage of our architecture? From an ISV perspective, are the applications being written in a way to take advantage of our architecture? It's an x86 processor, so it's going to run on your applications you're running in your data center, but we want it to be as optimized as possible. And then from an IHV perspective, so, working with folks like Mellanox and Samsung on the drive and memory side, we have a partnership with NVIDIA. And so, it's really, we believe that, through the open innovation and open partnerships, again, yes, we think the silicon is really important and it is important, but we need to have that ecosystem to continue to push the market forward. And that's our commitment to our customers. And then lastly, I'm a CPU guy. I'm part of the CPU server business unit, but we have some pretty awesome technology on the GPU side from an accelerator standpoint. And so, we're looking to maximize that potential to really, the bringing together of that, the CPU and GPU technology into tightly coupled type systems. So we want to make sure that we're doing everything we can to maximize that potential. And that starts with, technology alignment around our roadmaps, code development efforts in our labs, and then looking for every last bit of differentiation that we can extract from the marrying of those two technologies. As we look at the workloads that are being run in HPC today, clearly they're diversifying. People think classic HPC is, scientific research, whether you're talking, from universities or labs, things like that, and that's not slowing down at all. That continues to accelerate. But we're starting to see the boom in other types of workloads. AI is huge, and there's constantly lots of research being done on that. Modeling and simulation, especially in the manufacturing space and in the commercial space. Think of automotive and aerospace companies. huge diversification of HPC workloads there. And then from a big data standpoint, clearly, the amount of data that is being consumed, amount of data that's being generated and analyzed, they're starting to, take on more HPC characteristics of, okay, what do we do with all this data? How do we go about analyzing it? Those types of workloads are taking on more of your classic HPC type of architectures and characteristics from a deployment standpoint. And if there's one piece of feedback we get from customers when it comes to compute needs and those types of workloads is that you can never have too much compute. So that's kind of the mindset we take when we're looking at our roadmap out over time is, hey, we can never have too much compute. What can we do to continue to move that slope up and to the right? As a general rule of thumb, every 2.5 years or so, there's a doubling of performance expected, and so that's kind of the bar we're looking to. How do we continue to move that up and to the right, and don't change the slope of that curve? And so, years ago when we were looking at our roadmap and mapping out 3-4 generations of product, we kind of came to a crossroads of, okay, looking at the types of process technologies we're going to be using in the future, 7 nanometer and beyond, how can we design a product that is going to continue to deliver the performance expectations that you see on the chart here, right? How do you keep moving up and to the right, roughly, 2x every 2.5 years? And so we said, okay, well, if we design products that the market kind of knows and understands today, that kind of monolithic design where you have a certain number of cores on a die and you put it on your CPU, we're going to kind of run into a wall in terms of how we're going to be able to scale the number of cores and the overall capability on a CPU. And so we're kind of at a crossroads. Okay, how are we going to do this differently? Because we're clearly going to hit a wall when it comes to manufacturability of a product that's going to have 40, 50, 60 cores on it on a single die. We don't see that as being a viable option from a business case standpoint. And so what we came up with was what the architecture we've deployed today that we've had in market. We had a version of this with first generation EPYC, but what you see in front of you here is something that we've had in market since 2019 with the second generation EPYC that was codenamed Rome. And we call it AMD Infinity Architecture. But what it is basically breaking up a larger problem into smaller problems. So it's you can imagine that engineers came up with this idea, right? So we call this chiplet technology. And so you have easy to manufacture 8-core die on a package. So everything you see there that says CPU are 8 cores, and I'll show you the kind of the cache complex, but you have your cores and your cache on one of those CPU die. And then you have a centralized, what we call an IO die. But it's more than just IO. It's your PCIe and your legacy IO, but it's also your memory subsystem, your security subsystem, and it's centralized on that SoC package. And it's connected via a low latency, high bandwidth fabric that we call the Infinity Fabric. It's connected, the centralized IO die is connected to each one of these CPU die on the package. And so that solves a lot of our problems when it comes to being able to scale. So obviously, you came up with this cool architecture. Are we going to actually scale and see the performance as you add chiplets onto a package? And so this is an architecture that scales very, very well from low number of cores. We go down to 8 cores all the way up to 64 cores on a package. So now we've solved the problem of being able to scale performance, scale capability in these advanced technology nodes. But at the same time, we've added unbelievable flexibility into how we build products. So imagine each of these CPU chiplets as a placeholder, and we can populate or not populate chiplets on the package depending upon the type of part we want to build. So do we want to have a low end part with low number of cores and a low price point? Okay, we don't need to populate more than 2 on a package. So we can get to varying levels of core counts, cache levels, cost points, with this type of flexible architecture. So it's highly configurable. It's very much optimized from a performance per watt standpoint, but it delivers the overall performance and scalability that we need to address these high performance markets. And it's not just HPC is certainly what we're talking about today, but anyone that's doing any sort of like large scale deployment. So you think of like cloud deployments where you're trying to host a lot of users on a system, or VDI deployments where you want to have a large number of virtual desktops, large virtualization scenarios. So it's not just a benefit to HPC. Certainly there's lots of benefit to a huge number of a large amount of compute, but there's a lot of other benefits to this, a lot of other workloads that benefit from this technology as well. Digging into a little more detail, I'll actually go back real quickly. So each of these, where you see CPU on it, that's what I call a CPU chiplet, or a CPU die or core die. Depending upon the generation, this is kind of under the hood of what each of those little chiplets look like. So your second generation and your third generation are what you see in front of you. Similarities in that they are both 8 cores per die. You don't see the L2 cache here, but they have a dedicated L2 cache for each of those cores. With the second generation product, you have a total of 32 meg per chiplet, but that is broken up into 16 megs of L3 cache shared amongst 4 cores. On the third generation EPYC, you have a shared 32 meg, same total net cache, but shared 32 meg cache per 8 cores. And so that's actually another difference here that isn't labeled. But on second generation, these CPU cores are second generation Zen cores. Code name of Zen, it's just the code name for our cores. We moved to the third generation core with the third generation Zen core with the third generation EPYC. So with that brought pretty substantial IPC, or instruction per clock, uplift from generation to generation. But one of the benefits here of this cache structure is now we're able to build products. It gives us even more flexibility. So you saw the previous slide. We can mix and match, the number of cores, the number of chiplets that we put on a package. This gives us even more flexibility to build parts that have, extremely large amounts of cache across the spectrum of CPU core count. So we can build parts with 8 cores with the full complex of cache. So you populate, all 8 of these chiplets on a package, you get 256 meg of cache in a single processor. So you'll see our stack in a second. So we have, spanning from, the 8 core product all the way up to 64 cores with various core counts in between, having the full complement of 256 meg of cache available. And that's proven to be very beneficial for memory-bound workloads. So specifically things like computational fluid dynamics, things like weather codes that are memory-bound, having that huge L3 cache takes some of the pressure off that memory bandwidth. You're able to fit more of that job into that cache, and you really get some higher performance because of it. So from a feature set perspective, you can imagine, 8 cores per CC, or sorry, per die. We can get flexible in, turning cores on, turning cores off, how many chiplets we populate. So there's a lot of configurability that you'll see when you see the product stack in terms of the amount of cache and things like that. But from a feature set perspective, what we bring to the table is leadership across a number of areas that are key for high compute environments. First and foremost, think about 64 cores per socket. If you're looking at and you're concerned with overall, just raw throughput, raw performance, you've got multi-threaded applications, or you've got capacity HPC. We talk to tons of universities or research facilities that they're servicing thousands of users. They're running hundreds of applications, and people are basically signed up for time on their cluster. Being able to have 64 cores at a CPU level gives you tremendous scale out capability to be able to address all those types of users. But there's some customers that are more concerned with the speed of each of the applications and the per core performance. How much performance is my specific application getting? That's where our strong performance of these Zen 3 cores comes in. So not only do we have a raw throughput advantage at a socket level, we have outstanding performance per core. So whether you have a single threaded application, or maybe you're paying for software that's licensed by core, and you're trying to get the maximum or maximize your investment of that software, being able to eke out every last bit of performance from that core is really critical. So we have fantastic core performance with the Zen 3. Memory channels. So we've had 8 memory channels since we launched the first generation of EPYC back in 2017. I've been at AMD a long time. I remember in the Opteron days, memory bandwidth was always a critical consideration for us when looking at our roadmap. And so, we made it a point of emphasis for EPYC. So we've had 8 memory channels on our products since the first generation EPYC in 2017. It was an absolute differentiator for us, and we got a lot of wins in those memory bound type codes. So a lot of CFD type applications. We had a lot of early wins. And it's something that we continue to promote and innovate on that in that area. From a I/O perspective, we have 100 up to 128 lanes of PCIe Gen 4 per socket. And so, when you look at that type of I/O density, that's unique in the market. So, you got some customers that, certainly they're running, 2 sockets on a node because they're getting the most compute, but you have some customers that are running more I/O bound applications, and so not everything is compute bound. So being able to have that I/O density coming out of a single socket, there's some very, very efficient single socket platforms out there that still have tremendous I/O capability with those 128 lanes. So whether you're, attaching GPUs or you're attaching a lot of NVMe drives for storage and some sort of, high performance storage configuration, it's really an incredible capability just to deliver very efficient, high performing products in a single socket. And I've mentioned the cache. So, up to 256 meg of L3 cache. This has been proven to be a very much a differentiator for us. So for those memory bound codes, having the addition of the large cache takes a lot of the pressure off the memory bandwidth. And so we actually have a number of studies we've done that measures, how much benefit do you see from the cache. And there's actually a pretty cool one. I put a link on there, and if you get access to these slides, you'll be able to click on it quite easily. But we've shown, what we call superlinear scalability of the CFD application. So we looked at a variety of codes, like, some of the ANSYS suite, OpenFOAM. So, think CFD. And what we've shown is, running a job on a single node, normalized to a performance of 1. When you run that same job on 2 nodes, you get a little bit better than 2x performance. When you run that same job on 4 nodes, you get something like 5x performance. And when you run that job on 8 nodes, you get, anywhere from 10 to 12x performance. And so what's happening there is that, you've got more resources available. You loaded up the number of nodes, you're running that same job, and a lot of people think, okay, well, with added nodes comes added latency, but being able to have that large L3 cache, you're able to put more of that job into the L3 cache, close to the computation part of the system that's going on, and it's enabled that superlinear scaling. So that cache has been a real differentiator for us, specifically in HPC. And then from a toolchain perspective, our commitment to open source. We have a clear, put in a lot of resources and investment into the toolchain ecosystem, but we have a clear strategy when it comes to, delivering optimized compilers, AMD compilers that's based off of LLVM, but, optimized. The libraries that we use are open source libraries. We have power and profiling tools. So we're making tremendous strides in this area. We certainly know that we have a fierce competitor when it comes to the toolchain ecosystem, but we've made tremendous strides and we get very, very good performance on our toolchain. Quick note on who's deploying EPYC, because that tends to be a question a lot of people ask us, especially when they're kind of new to AMD. Certainly from an HPC perspective, research and academia has been very, very strong for us. With first generation EPYC, we had a very, very from a product perspective, it was not what I call, it wasn't a flops monster, so it wasn't going after those top 500 type opportunities, but it was very strong in some key components such as, core density, memory bandwidth, I/O. So we had a lot of wins in the commercial space and academia space for, smaller clusters and the hundreds of nodes type of thing. As we've progressed through our roadmap, starting with second generation in 2019, that really opened the aperture in terms of the types of HPC wins that we could go after, because we doubled the cores, we quadrupled the flops. A lot of those things that these big, supercomputing type of opportunities are going to value. And so that really is where we started knocking off a lot of these larger wins. So we've had been very successful in weather modeling, and just large scale, general, quote unquote supercompute type of opportunities. You see up there Frontier and El Capitan. Those were the future deals that were announced, that are 2 out of the 3 future exascale systems. Sorry, I always have trouble with that word. That have been announced as part of the U.S. Department of Energy. that is actually using AMD CPU and GPU technology. So that's really seeing the benefit of those two technologies being used together. So very strong in research and academia. We have a rich history there going back 15 years with Opteron. But we also have been very strong in commercial. So, looking at oil and gas customers. By the way, this tends to be an area where those customers don't allow you to use their logos, but we can talk about verticals and things like that. But we've been a number of wins in oil and gas, consumer goods. So looking at different packaging and how that affects, looking at how that affects how they're packaging, the design of that packaging, how that affects shipping and everything that goes with it. Aerospace and automotive have been quite strong. Again, that's real heavy on CFD codes and finite element analysis. I guess government isn't really commercial, but I put it on here anyway because it's not research and academia, but very strong in the government space. Media and entertainment has been one. You think of rendering, where that's very parallel application, likes a lot of cores. That's been strong for us. And then financial services. So think not necessarily high frequency trading, but think more of the compute grid where they're doing, the high performance computing analytics, and a lot of that is proprietary software, proprietary codes. So a lot of POCs there to see how their applications, run with our hardware. We've shown very, very positive results there and have a number of big wins in that space as well. As by the way, you see these verticals, and we're talking about HPC. So yes, we have wins in all these HPC spaces, but we also have wins in the more enterprise IT type applications at all these types of customers too. Because if you're good for HPC, that means you can handle compute capabilities. And so everyone's looking at us for your big data, your Hadoop, large scale virtualization, things like that. There's a very, very good value proposition we have around performance and how that leads to a lower TCO for a wide variety of applications. So yes, I know we're talking about HPC, but every organization has other parts of their IT department as well. So we're not just a niche HPC customer or HPC vendor. I already mentioned Frontier. This is one that is going to be deployed later this year. It is breaking the exascale barrier. And again, this is an AMD CPU plus AMD GPU system that's going to be deployed. Cray won it. HPE now Cray won it with our hardware. So this is one that we're eagerly anticipating. It's going to be pretty cool, and I think one that's going to opened a lot of people's eyes when it was announced, and we'll continue to do that when it's deployed. Real quickly, a note on, I'm not going to sit here and throw a bunch of benchmark charts at you, but just kind of making the point of what I mentioned around overall compute and then performance of those cores. So looking here at kind of a generic HPC type of benchmark, spec FP rate base. And I know it says here highest published scores as of 416. I actually checked this a couple days ago to make sure it was still the same. So over on the left, you look at kind of in the gray box on the far left, the latest and greatest from our competitor with their Ice Lake product, the 8380. That's where they kind of top out at 40 cores. And by the way, that's a great proof point as you look at our architecture. They're still kind of on that monolithic design using those advanced technology nodes. They're topped out at 40 cores. Our solution to the problem with that chiplet technology, AMD Infinity Architecture, combined with the 7 nanometer technology that we use from TSMC, up to 64 cores. So that's a great proof point on our technology, and that chiplet and Infinity Architecture was the direction to go. But if you look at overall throughput, a 472 score, this is spec FP rate base. If you compare that to where we were with our second generation product, the one that's been in market in 2019, we still have a pretty substantial lead. That's kind of the middle bar here. And if you look at what we just launched about a month and a half ago in mid-March, the third generation EPYC, we extend that lead. So, if you look at a kind of a spec sheet of second and third gen EPYC, they look fairly similar from number of cores and memory bandwidth and things like that. But we did a lot of things under the hood, including moving to the Zen 3 core, which brought a lot of extra performance. So you can see we kind of doubled down on the performance part of that value proposition, moving to second to third generation. So from a total socket throughput, almost 40%, 38% on this particular benchmark of a total throughput. But then a lot of people say, okay, well, yeah, but that's okay. You've got more cores, but their cores are really strong. Okay, well, let's look at a same core count to a same core count product, and you can see that they're just not quite, but you can call it pretty close to where we were with our second generation product, and then we raised the game, raised the bar with our third generation EPYC. Pretty substantial performance uplift if you look at per core performance on this particular benchmark. So 25% faster than our competitor at the same core count. So whether you need raw compute throughput at a socket level, or you need some sort of a balance of good core density with good core performance, like a lot of people typically buy the 32 core product for, we've kind of got you covered. So you got the best core performance, you've got the best performance at a socket level. It just kind of gets down to what are the particular attributes and particular applications you're running to figure out which makes the most sense. I'm not going to go into painstaking detail on this one. A couple of key points. One is that we take a stance, and we have even back in the Opteron days, but certainly since we launched EPYC, where what I call the Uncore feature set. So things that everything that's found in that I/O die. So your memory speed support, number of memory channels, your I/O support, security features, whether or not turbo is enabled, all those things. We want to make the buying process as simple as possible. So we don't want customers to have to, get out a big chart and say, okay, well, I wanted that memory speed, and I wanted that feature, and I wanted that feature. That means if those three features are important to me, I can buy one of two SKUs. Like, no. Everything that's Uncore is going to become included, whether you're buying the lowest 8-core part or the highest 64-core part. So where we differentiate our SKUs is, the number of cores, the speed of those cores, the total cache, because this is, depending on how we build a part, the cache levels could be different, and then power. And so it really comes down to what's the right type of compute you need, and are there power and budget constraints to consider. And actually, that budget's the other thing. So price, obviously, there's differentiation on price, but what's the level of compute? What are the power and budget constraints that you need to consider? All the other stuff, you don't have to worry, that comes included in the product. So trying to make it as simple a process as possible for people. I've mentioned toolchain a couple of times. Just a quick note here. Our performance compiler is called AOCC. This is the AMD optimized CPU compiler. It is based off of LLVM. So we take the LLVM kernel, we make our own modifications and optimizations around it, and we release that as AOCC. Over time, some of those optimizations make it back into the LLVM community, the LLVM kernel. Not all of them, but some of them do. And then we have a regular cadence. When LLVM release comes out, we take it, we add optimizations, we release ours. And so it's very, very rigid in terms of a schedule. From a library perspective, it's very much an open source strategy. By the way, the compiler and the libraries are available on AMD, developer.amd.com. So these are things that we make readily available. We don't necessarily charge for. And we have also released in the last couple of months something called ZenDNN, which is a CPU inference acceleration package, software package. So again, continuing to innovate and invest on the software side of things. And then from a profiling perspective, we have something called microprof or uprof that is performance and power profiling. This is a bit of an eye chart, but it's a point I want to make, and I kind of made one about the ecosystem earlier. But just to give, and this isn't everyone we work with or every application that works, but just to give you an idea of kind of our take on the situation. We understand that yes, we're a hardware company, and we make really cool technology, we think, but it takes a village, and so we work with a lot of great partners in the industry. You kind of look over here at some of the IHVs that we work with in OS to make sure. Tight engineering relationships to make sure that things are as optimized as possible. Then over here, kind of on the right-hand side, you see a lot of our featured HPC ISVs that we work with. Excuse me, I had a cough there. And we're lucky enough to have Ansys here. Ansys is certainly one of the more important ones that we work with, just based off of the types of customers. There's a lot of customer overlap between who we call on and have relationships as well as them. So certainly they're a focus for us. But the point is, we really want to work with the entire ecosystem to continue to innovate and provide value to customers. Continue to accelerate that value, accelerate the types of cool stuff that our customers are doing, because that's really kind of why we're all in this to begin with. So with, oh, actually, yeah, roadmap. So there's probably interest in roadmap. I thought it was finished. So I'm not going to dwell too much on the past here. Just from a timeline perspective, our first generation EPYC was made with our first generation Zen core, what we call Zen. It's just our code name for the core itself. That was released back in middle of 2017. The second generation EPYC was released in 2019, and again, that's where we really started to kind of open the aperture and the types of wins we were going after in the HPC space, got into a lot more of the larger supercomputers, as well as enterprise as well. So, enterprise kind of takes a little bit longer. There's longer POC cycles, things like that. That second generation, 2019, is when you really start to see the slope kind of go up in terms of market share. And then we have launched our third generation EPYC as of middle of March. So we are in market today. Certainly performance advantages over second generation. But I'm for one happen to think there's going to be a fairly long tail on second generation EPYC. It's still, you saw from some of those benchmarks, it still has a very good value proposition from just a raw performance standpoint, from a feature set standpoint. So I think there's going to be opportunities for customers to get some great value on using second generation EPYC technology to run their workloads, because it still does have a very strong value proposition. But for customers that want the latest and greatest and absolutely put an emphasis on having the best performance, third generation EPYC delivers that. Moving forward in time, I'm not going to go into much detail on fourth generation, but know that we have a strong roadmap for the future. We have a defined roadmap for the future. So if we happen to have NDAs, you can certainly reach out after, and we're happy to kind of go through more detail should the circumstances be right. But we want to make sure we're under NDA. But the fourth generation product is codenamed Genoa. We will be moving to fourth generation cores, the fourth generation Zen cores. And so again, we're never going to take our eye off the ball. We want to keep moving that roadmap up and to the right in terms of capability. It's a compute-focused roadmap, and feedback from our HPC customers has been very, very strong on our future roadmap. So certainly happy to have those conversations with people. So that's kind of where we are in terms of product evolution. We've got the world's fastest server processor. We've got broad industry adoption and continue to work, not just adoption from end customers, but continue to work with our OEM and our ISV partners to deliver optimized solutions to the market. We believe we have a very differentiated feature set, and we continue to focus on that with our future roadmap that we think is a very strong story for the foreseeable future. So I appreciate the time.